on blockchain definition to clarify its role for the Internet of Things. Abstract. The term of blockchain is used for disparate projects, ranging from cryptocurrency to application for the Internet of Things (IoT). The concept of blockchain appears therefore broad, as the same technology cannot infer the implications with extremely different requirements, levels of security and performance. This position paper elaborates on the theory of distributed systems to advance a clear definition of blockchain, allowing us to clarify its possible role in the IoT. The definition binds together three elements that, as a whole, define those unique features that distinguish the blockchain from other distributed ledger technologies: immutability, transparency, and anonymity. We note that immutability, which is imperative for securing blockchains, imposes remarkable resource consumption. Moreover, while transparency demands no confidently, anonymity enhances privacy but prevents user identification. As such, we raise the concern that these blockchain features clash with the requirements of most IoT applications, where devices are power constrained, data needed to be kept confidential, and users to be identifiable. We consequently downplay the role of blockchain for the IoT. This can act as a ledger external to the IoT architecture, invoked as seldom as possible, and only to record aggregate results of myriad of local IoT transactions that are most of the time performed off-chain to meet performance and scalability requirements. Introduction. The blockchain came into the limelight with the advent of the Bitcoin, which is the most successful blockchain applications to date, hitting a US $1 trillion market capitalized in February 2021. A new record some features observed in Bitcoin, i.e., for example, decentralized resistance to powerful cyber attacks and prevention of user privacy, raised the enthusiasm of the communities, leading to an explosion of disparate proposals for using blockchain in many different applications comprising supply chain management. First, e-voting, smart grid, healthcare, banking, smart cities 6 and 7, and even vehicular and aerial networks. To name a few, survey focusing on the application of the blockchain for the Internet of Things (IoT), for instance, already abound 10-11. This vast application range makes the blockchain look like an almost universal technology. We note, however, that the original Bitcoin blockchain supports less than 10 transactions per second (TPS) and consumes as much power as Ireland. It is therefore unclear how a similar blockchain will ever be so versatile to support all of the documented applications, especially the IoT ones involving millions of TPS and tight power constraints. Indeed, moving to application domains different from cryptocurrencies, the characteristics of the original blockchain have been completely transformed, leading to mutated blockchains that are possible source of misunderstanding and confusion. On the other hand, we still have permissionless blockchain like the original Bitcoin, celebrated for their proof of work (POW) based cryptocurrency security, their decentralized and strict vacancy defense through anonymity. On the other hand, many more recent blockchains are permissioned, require user identities, and their internal security does not depend on some hard cryptographical problem such as POW. The single term blockchain appears therefore overloaded, resulting ambiguous as it is used to indicate ledger technologies that address security, performance, and decentralized in completely different ways. This position paper analyzes the multiple technologies proffered under the term blockchain from distributed system perspective, and proposes a clear definition of blockchain that allows arguing it its role in the IoT. Our definition identifies the three elements that only when combined together give to blockchains their specific features of openness, decentralized security, and privacy. Strong distributed consensus protocol, which makes the blockchain immutable and frees them from centralized trusted authorities. Full and public history of transactions, which allows their distributed and completely transparent validation. And 3. To be open to anonymous users, allow complete user privacy. To convey our crucial blockchain definition and the argument on the blockchain role in the IoT, this paper is structured as follows. Section 2 critically analyzes the genesis of the blockchain, stressing on the technical reasons motivating the design of the blockchain like Bitcoin. Section 3 discussing the trade-off inherent to the design of the consensus protocol that are key for determining the properties of the shared ledger, either blockchain-based or not. Section 2 and 3 are basis for the formulation of our blockchain definition, reported in main section 3. In section 4, in the right of provide definition. In section 5, we outline the marginal role we envision for the blockchain in IoT. An extended version of the paper available on Archive 13 includes a more complete background with a review of the consensus protocol as well as discussed about what we call the blockchain pitfalls. For example, does common abuse of the blockchain in application whose requirement constraint with the feature of the same blockchain. Moreover, it contains an expanded section on the possible applications of the blockchain to the IoT without violating its constituent characteristics, omitted higher space constraint. Figure 1. Blockchain fundamentals illustrates generated life cycle of the transaction in blockchain system. A user that issues a new transaction announced in the peer-to-peer network and waits for the correctness check performed by validator nodes. These nodes run a consensus protocol to determine if the issuer owns the resources it is spending or not. A transaction that is considered valid is grouped with others to form a new block or transactions, and this block later registered in the ledger by appending in its blockchain. At the end, the success of the transaction is notified to the users. First, figure 1. Processing a transaction before storaging in the blockchain. At a glance, the blockchain may look at as a plain data structure used to record transactions. However, from the broader perspective, a blockchain is a distributed system that includes item September 0 EM, left margin 0.5 cm, a P2P network made of all those nodes that either reads or cooperatively write transactions in the blockchain, and a consensus protocol, namely a set of policies agreed upon and implemented by all nodes, which are the rules that regulate which and how new transactions can be added to the blockchain. A blockchain can thus be seen as a possible implementation of the shared ledger, which can be either public or private depending on who allows to appending new transactions to the blockchain. Public and private ledgers. In public permissionless ledger, the record of transactions is public and the consensus protocol is open to anybody. This means that anyone in the world can be verify the correctness of the ledger. And the second, even anonymous stranger without explicit permission can join the network and participate in the validation process of transactions. Users are thus not accountable, and the security must be enforced through the technical solutions. For example, a permissionless blockchain such as Bitcoin and Ethereum, the anonymous proposer of a new block must provide a solution to a very hard crypto problem, the so-called proof of work (POW). On the one hand, The POW proves the honest commitment of the proposer, but on the other hand, it hampers performance and garbage computation resources. Private permissioned erasers allows as an attempt to improve performance and have a more control on users. A shared and mutual level of trust given for granted, as only registered hence accountable entities have the permission to write data into blockchain. The security of permissions blockchain depends therefore on classical authentication mechanisms. The resulting model allows blockchain measures to replace the resource-hungry consensus protocols of permission. Permissionless blockchain with more traditional, efficient, and faster ones. The needs of the transaction history. Validators need the history of transactions to determine who owns resources and how many. However, building this history in the distributed system is complicated by the double spending problems. This problem arises from transactions that spend the same resources twice, but are received by distinct validators in diverse orders because of different propagation delays. Validators need to run a consensus protocol for sorting transactions into a unique canonical order, fundamental to determine which among two conflict transactions should be considered first valid and which other second rejected. The blockchain captures this canonical history of transactions necessary for validation purpose by grouping transactions in time-stamped blocks. Unfortunately, the transaction history may not be enough. Indeed, a malicious user can alter the contents of block, repudiate unwanted transactions, falsifying this way the validation procedure. To fend off falsification attacks, a blockchain must be tamper-proof and immutable. The tamper-proof property is achieved by the clever embedding of cryptographic hash functions (CHF) into blockchain data structure, while the POW makes the blockchain immutable as well. The proof of work. The Bitcoin protocol dictates that a block is valid only if the application of the mandated CHF, for example, double SHA-256 to the block content procedure, a digest smaller than given target. The smaller the target, the higher will be the required number of leading zeros in the most significant digit of the digest. A number of we call Z. Notice that the double SHA-256 procedures digest of 256 bits, and that a miner can include an arbitrary piece of the information in the block. The nonce to influence the result of CHF, the probability for the random nonce to read a validated digest can be approximately computed as a function of Z, resulting to be equal to Pn 2 minus Z, the number of Z indicator of the mining difficulty, and can be adjusted to tune the generation rate of validated blocks. Finding a validated nonce is a proof of works (POF). For example, the proof of the effort in terms of computing power and the energy spent to finish such a nonce. Block generating propagation and forks. Bitcoin targets an average block generation interval (BGI) of 10 minutes. Figure 2 reveals how the growth of the network computing power over the time, resulting in the need of dynamically adjusting Z to keep the desired targets (BGI). The BGI must keep kept high to avoid the production of the simultaneous blocks. The blocks are considered simultaneous if the second one is generated within the average block propagation time (PB) of the first one. In general, the PB of the blocks of a few megabytes in any P2P overlay is in the order of seconds, the maximum of the new tens of a second. 14. Simultaneous blocks divided the nodes of the Bitcoin network into two parts that will append the two different blocks to the blockchain, forming two branches, a fork. The existence of the fork means that there is no consensus on the order of blocks, for example, transactions. Therefore, the system is again exposed to Figure 2. Evolution of the Bitcoin network computing power measures in hash per second. Over time, the block difficulty has been adjusted to keep a constant block generation intervals, BGI. Statistics are taken from www.blockchain.com. Double spending attacks usually force our transitions and are cleared as soon as another block is presented, making one branches longer than other. In general, validators will prefer and give their consensus to longer branches because of the so-called longest chain rules. According to the rule, only the blocks of the longest chain are valid, while the blocks on the tail branches are not, meaning also that validators that want to gain the Bitcoin rewarded by submitting valid blocks are encouraged to dedicate their computational power only to growth of the main chain. One intrinsic limit of a blockchain is the presence of a propagation time necessary to distribute the knowledge of a new created block in the peer-to-peer network of miners. Assume that all miners are computing to the mine block BI, and at the time Ti miner generates the block. After BP seconds, all the miners know that they should stop mining BI and start mining BI plus 1, but the time interval Ti plus BP, miners are using resources to mine a block that will most likely not enter the blockchain. As an example, BP to reach 90% of the Bitcoin miners in order to 10 of seconds. One goal of the blockchain is thus to reduce the relevant amount of wasting resources that depends on the ratio between BP and the average block creation time BGI. This is referred to as a blockchain overhead. 16. A large BI is essential to maintain a lower overhead and prevents the deployment of fast blockchain, POW, and immutability. Consider a malicious user that wants to cancel an unwanted connection form, let's say block I. This alternation would invalidate block I digest and due to blockchaining, or the following ones, so that all validators would immediately notice the manipulation and refuse the tempered branch. Another attack strategy exploits the longest chain rules and consists in generating longer branches of blocks that replace the previous one starting from block I-1. This attack is usually referred to as a 51% attacks, as it becomes likely when some miners owns the majority of the miner's resources. So it is extremely important that mining power is not monopolized by one or more coalition of miners. The limits of the consensus protocol. Section 2 poses the distribution consensus problem on the order of the transactions and explained how the POW solves it. It turned out that the POW must be necessarily power hungry to make the cost of chain replacement attack prohibits. In general, the POW advantages are many. It is secure, fully distributed, and user agnostic. Ultimately, the POWI protects the user privacy and, second, frees user from trusted authorities. The popularity of blockchains above all with cryptocurrencies is most probably grounded in these two key aspects. It can be observed that consensus protocols are a crucial component of shared ledger, performance consistently, policies of governance, security, and tolerance of failures are all properties of shared ledger that dependent on the selected consensus protocol rather than on the data structure used to record transactions. However, a question arises: it is possible to design consensus protocol that preserve the paired advantages, but at the same time avoid its drawbacks to meet the typical requirements of the IoT applications. In the rest of this section, we briefly review the theory of distributed consensus protocols, reviving those theorems that limited the design of consensus protocols for blockchain in general, representing crucial bounds, especially for IoT applications. We omit a full review of consensus protocols, which is available in 13. The CAP theorem 18 is a pillar of the theory of distributed system and stated that whenever a system gets partitions, the only two options are available: grant consistently by safely blocking the system fix failures, keep processing transaction favoring availability, with the risk that the two conflicting double spending transactions could be recorded, one per partitions. The CAP theorem may be considered only middle relevant since it is validatory only for ill-behaving systems, while in practice system is built to work properly for most its lifetime. However, it is the afternoon for definition of two trade-offs of tremendous practical importance. The first trade-off is known as parser, which advances the CAP theorem, solving the acronym adding, else latency or consistency. The parser theorem focused on the trade-off between latency and consistency arising from the propagation delays in scalable for any distributed system, thus varied also not partitioned systems. In section 2, we have analyzed the Bitcoin design's choices to calibrate this trade-off, showing how Bitcoin clearly favors consistently over availability by setting the quiet high BGI of 10 minutes then, together with the 6 confirmation rule, introduced a large delay over transaction is leisure. The second trade-off is known as blockchain trilemma. It's illustrated in Figure 3, which is essentially the reformulation of the parser theorem for the blockchain domains. In particular, trilemma illustrates the conjecture that blockchain system cannot, using maximum decentralization, security, and scalability performance, at the same time limited by the trilemma. An IoT developer willing to improve the network scalability may choose consensus protocol less expensive than POW or reduce the mining difficulties to speed up the block generate rate.